It's my pleasure to welcome Daniël Thung from the University of Hamburg, who will speak on cohomogeneity 1 quaternionic Kähler manifolds.
Thank you very much for the introduction, and thanks to the organizers for giving me the opportunity to give a talk, and more generally for organizing this great seminar. It's really been a pleasure to follow along for the past, well, year or so. So thank you very much. Okay, with that said, let's get started. As you can see, the topic for today is cohomogeneity 1 quaternionic Kähler manifolds. So I'll start my talk off by giving a brief recollection what is a quaternionic Kähler manifold and discussing some of the known examples of quaternionic Kähler manifolds. This will naturally lead us to the CMAP construction, which is a differential geometric construction, which has been used in recent years to construct many new complete examples of quaternionic Kähler manifolds with negative scalar curvature. And once I introduce the CMAP in some detail, I will continue to discuss how symmetries of the resulting quaternionic Kähler manifolds can be studied and discuss their symmetry properties. And in particular, I will focus on explaining how one can construct cohomogeneity 1 quaternionic Kähler manifolds using this construction. In the final part of the talk, I want to discuss a little bit about some discrete quotients of these manifolds, which can have interesting volume properties. So the work that this talk is based on is contained in 2 papers with Vicente Cortés and Arpan Saha, and also 1 paper with Vicente Cortés and Markus Röser. Okay, so let's get started and jump right into the definition of a quaternionic Kähler manifold. This is a Riemannian manifold whose dimension is 4n, where n is a natural number at least equal to 2, whose holonomy group is contained in the subgroup SBn, SB1 of S of 4n. So what this means is that quaternionic Kähler manifolds are manifolds with special holonomy, and therefore also appear in the famous list of Berger, which lists all the possible holonomy groups of complete Riemannian manifolds, which are not locally symmetric. As many other entries in Berger's list, quaternionic Kähler manifolds have interesting curvature tensors. In fact, they're always Einstein, but what sets them apart among all the entries of Berger's list is that they are always Einstein, but not always Ricci flat. So in fact, a quaternionic Kähler manifold is Ricci flat if and only if it is already locally hyperkähler. This case will be mostly left to the side in this talk, so we will focus on the case of non-vanishing scalar curvature or Einstein constant. Okay, so Berger's list was taken by many differential geometers in the 20th century as a challenge, namely to construct explicit Riemannian manifolds whose holonomy groups fulfill or check off the entries of his list. Right, so this construction project of finding manifolds with special holonomy of all the different possible types, it's been one of the biggest problems and undertakings of the second half of the 20th century in differential geometry. And it's been very successful. And due to the efforts of many, maybe even thousands of mathematicians, we now have compact examples of every type, which are not locally symmetric, except in the case of the quaternionic Kähler holonomy groups SBn, SB1. So this is perhaps the largest and most important open question in the field today. And do there exist any compact quaternionic Kähler manifolds which are not locally symmetric? Now, given that this is still open, and what is known about it, let's check a little bit about examples of quaternionic Kähler manifolds. Here we have the case of positive and negative scalar curvature. The first case of positive scalar curvature is very rigid. In fact, it is believed and conjectured by Lebrun and Salomon that no non-symmetric examples of this type exist at all. And in fact, this is a theorem in dimensions up to 16 already. So one does not expect to find any non-symmetric quaternionic Kähler manifolds of positive scalar curvature. The case of negative scalar curvature, however, is much more intricate, subtle, and complicated. Here, it makes sense to ask for quaternionic Kähler manifolds which are complete but not compact. And it turns out that non-symmetric examples of this type can be found. In fact, the first of them were constructed in the 1970s already by Alexevsky, who found homogeneous quaternionic Kähler manifolds homogeneous under a solvable group, which are not symmetric and of negative scalar curvature. Moreover, there's a famous result of Lebrun from the 1990s, which asserts the following. Say we start with quaternionic hyperbolic space, which is arguably the simplest possible quaternionic Kähler manifold of negative scalar curvature. It's a symmetric space. And we look at deformations of this quaternionic Kähler metric. Then what Lebrun proved is that there's an infinite dimensional moduli space of complete quaternionic Kähler deformations of this standard metric. So morally speaking, what this theorem is saying is that the world of quaternionic Kähler manifolds of negative scalar curvature should be very large and wild. And so in principle, it should be possible to find many interesting examples with different types of properties. However, this vision hasn't really been realized. In fact, historically, it turned out to be really complicated and difficult to move beyond the original examples of Alexevsky and create new explicit examples. Here, Lebrun's theorem doesn't help because Lebrun relied on twistor theoretic methods, which do not allow one to explicitly reconstruct the quaternionic Kähler metric. Fortunately, however, the situation has recently improved quite a bit with use of the CMAP construction, which allows us to make many new examples which are complete of negative scalar curvature, and in particular allows us to go beyond homogeneous spaces, as we'll see in this talk. Okay, so given this fact about the CMAP, I want now to spend some time to introduce to you all the ingredients in this construction. And I won't start with the first step in this multi-step process. I'll start instead with the most complicated and, in my opinion, most interesting step of the CMAP. So this is the so-called hyperkähler quaternionic Kähler correspondence, or HKQK correspondence, as I'll refer to it from now on. The HKQK correspondence takes as input a pseudo Kähler manifold and turns it into a quaternionic Kähler manifold. It can be viewed as a special case of Swan's twist construction, which is a more general construction dealing with manifolds with circle actions. So, as I said, the input is a pseudo hyperkähler manifold, which I'll denote by n. It has a hyperkähler metric and Kähler forms omega 1, 2, 3. It is also endowed with a distinguished circle action, which is a rotating circle action, meaning that it's isometric and preserves one of the Kähler forms, while it rotates the plane spanned by the other two Kähler forms. So expressed in terms of the generating vector field, which I'll denote by Z, we have these four conditions. I'm also going to assume that the circle action is Hamiltonian with respect to the one Kähler form that it does preserve, and that this Hamiltonian, Fz, will be nowhere vanishing. Okay. In this general setting, we can always construct another two form, omega h, by adding an exact piece to omega 1. And this omega h has the interesting property that it's of type 1,1 with respect to all the complex structures defining the hyperkähler structure. Also, the circle action is still Hamiltonian with respect to omega h, and the Hamiltonian is obtained from the original Hamiltonian by adding this term. Okay, so what's our aim now? Our aim is to create from this n with circle action a new manifold n bar, which is a quaternionic Kähler manifold. And moreover, this quaternionic Kähler manifold n bar will be endowed with a twisted circle action. So let's see how this construction works, at least on the level of smooth manifolds. So I have this manifold n with circle action. The first step is to construct an S1 bundle over n, whose total space I'll denote by P. This P is a circle bundle, and the associated complex line bundle is known in terminology of Hitchin as the hyperholomorphic line bundle, because its curvature, it's equipped with a connection whose curvature is omega h, which is of type 1,1 with respect to all the complex structure, and is therefore called hyperholomorphic. So now we have our space P, which is a circle bundle over n, and it comes, of course, with the principal circle action here denoted in red. Under the assumptions we made on the original circle action on n, we can also lift the circle action from n to the total space of P. And in this way, we obtain a second circle action, which commutes with the other circle action and is now denoted in blue as 1 hat. So now we have two circle actions on P, and instead of dividing out the red circle action to obtain n, we can divide out the blue circle action and obtain another manifold, which we call n bar. This manifold is called the twist of n, and it inherits a circle action from the principal circle action on P. So in this way, we create a new smooth manifold. And this will be the smooth manifold underlying our quaternionic Kähler manifold in the HKQK correspondence. Now, the power of this twist construction lies in the fact that we not only can construct this new manifold n bar, but we can also study geometric structures on n bar in terms of the original geometric structures on n. So let's see how that goes. We have this double fibration structure on P, right? We have two fibrations here, to n and n bar, and we have a connection on P. And this connection, of course, defines a horizontal distribution in the tangent spaces of P. Now, this horizontal distribution is transverse to both the lifted and the principal circle action, and therefore can be pointwise identified with the tangent space to n and the tangent space to n bar. Using these pointwise isomorphisms, linear isomorphisms, we can compare geometric structures on n and n bar. So loosely speaking, we can take a geometric structure on N and we can horizontally lift it to P and then push it down to N bar. And the resulting geometric structure on N bar will be called the twist of the original structure. Of course, such a procedure can only work if the original structure we started with was invariant under the circle action, because otherwise, if you lift it to P, you will not get something invariant under the blue S1 hat in my previous diagram, and therefore you will not get something well-defined when you push it down to N bar. So in this way, this twisting sets up a bijection between, in particular, S1 invariant tensor fields on N and on N bar. This bijection has some very nice properties. In particular, it preserves all algebraic properties of tensor fields. So if I started with, say, a Riemannian metric, then its twist will always also be a Riemannian metric on the twist manifold. However, it doesn't preserve all properties of the geometric structures. It destroys, in general, any kind of differential condition. For instance, a closed form upon twisting becomes a non-closed form in general on the twist manifold. Or an example which we will need later on, if I have a killing field on N, and I twist the metric and the vector field, then the resulting vector field will not be a killing field with respect to the twisted metric, because this is a differential condition which is destroyed by twisting. However, this failure to preserve differential conditions is controlled in terms of this twist data, which consists of the vector field generating the circle action, the two-form omega h, and the corresponding Hamiltonian fh. So it's a controlled type of failure, not a completely useless type of failure. Okay. So given all this, let's try to create a quaternionic Kähler manifold, right? The first thing you would try is maybe to twist the pseudo-hyperkähler metric that we started with. However, that doesn't work. And the reason why can be seen in terms of this failure to preserve differential conditions. So the hyperkähler geometry is an integrable type of geometry. And so upon twisting, you will destroy the integrability condition and will not obtain the type of integrability condition that is needed for a quaternionic Kähler manifold. So the hyperkähler metric does not actually twist to a quaternionic Kähler metric on N bar. However, we can modify the hyperkähler metric and obtain a quaternionic Kähler metric. And this is the content of the following theorem, the statement of which in this final form that I present here is due to Maciá and Swan. But there are also important other contributions from Heidis and from Alexevsky, Cortés, Diekmans, and Moab. So we start with our pseudo-hyperkähler manifold N, endowed with a rotating circle action generated by a vector field Z and a Hamiltonian function Fz with respect to the Kähler form omega 1. Then we, as I said, we do not twist the pseudo-hyperkähler metric to obtain a quaternionic Kähler metric. Instead, we have to twist a related metric, which is denoted by GH. This GH is obtained from G by first performing a conformal scaling, so multiplying our original pseudo-hyperkähler metric by a non-vanishing function, and then performing an independent conformal scaling along the quaternionic span of Z, which means the span of the vector fields Z, I1Z, I2Z, and I3Z. Then if we twist this metric with respect to this data Z, omega H, and omega FH, where omega H and FH here are recalled, but you've seen it before, the twist of this will be a pseudo-quaternionic Kähler metric. Moreover, we have control over the signature. In particular, if the initial hyperkähler metric I started with was of quaternionic signature n,1, and the Hamiltonian function is positive while fh is negative, then the resulting quaternionic Kähler metric on the twist manifold will be positive definite, so a Riemannian metric, and it will have negative scalar curvature. So this is a fact that we will use later on. Now, given all this, we see that the production of quaternionic Kähler manifolds with negative scalar curvature has been reduced to the production of hyperkähler manifolds of quaternionic signature n,1 with a rotating circle action of the prescribed type. And so the next step is to look for a source of hyperkähler manifolds of this type. And the source that we will use for the CMAP is called special Kähler geometry. So let's introduce a special Kähler manifolds. An affine special Kähler manifold is just a pseudo Kähler manifold, so I don't insist on positive definite signature, just an indefinite metric is allowed. But it is endowed with a distinguished connection, nabla. This is called the special Kähler connection, and we require it to be flat and torsion-free and also preserve the Kähler form. So nabla of omega is 0. However, it does not preserve the complex structure. We only require that the complex structure, when I take the covariant derivative, yields a symmetric bilinear form on the tangent space of M. In fact, we're not interested in arbitrary types of affine special Kähler manifolds, but only in those which are conical, or Kask manifolds for conical affine special Kähler. So what's a Kask manifold? It's an affine special Kähler manifold, which comes equipped with a distinguished vector field, the Euler field, denoted by psi. And the characteristic property of this Euler field is that its covariant derivative with respect to both the special Kähler and the Levi-Civita connection yields the identity endomorphism of the tangent bundle of M. And we will moreover require that the norm squared of this Euler field is negative, but that the metric at the same time is positive definite on the orthogonal complement of the Euler field and J times the Euler field. So we see that this Kask manifolds must be of signature n,1, complex signature n,1. We're also going to assume for technical simplicity that this psi and j psi generate a free and proper C star action on the manifold M. Okay, so given this C star action, we certainly have a circle action. This circle action is generated by j times psi. And one can easily check that in this setting, the circle action is always isometric and holomorphic. So in other words, it preserves the full Kähler structure. And given such an action, what one can do is to form the Kähler quotient. And this, by definition, will be a projective special Kähler manifold. So for us, a projective special Kähler manifold is the Kähler quotient of a Kask manifold by its distinguished circle action. In particular, if I'm talking about a PSK manifold, I always have to tell you which Kask manifold it comes from. So in the context of this talk, PSK and Kask manifolds will be used interchangeably. Okay, now this might be a lot to take in, so let's see a very simple example of how this works. Let's consider the standard permission form of signature n,1 on C n+1. So this induces, of course, a flat Kähler structure of signature n,1 as well. And we consider the open subset of points which have a negative norm squared with respect to this indefinite form, denoted by M. This is, of course, a flat pseudo-Kähler manifold, and because it's flat, the special Kähler connection and the Levi-Civita connection can be taken to be equal. So we take the special Kähler connection and the Levi-Civita connection both to be the trivial connection in this case, and we consider the Euler field, which is just the classical Euler field on a vector space. So psi is RdR, where R is a radial coordinate on the vector space. Now, all this data together defines the structure of a conical affine special Kähler manifold. And if we form the Kähler quotient, I guess many of you know that if you take the Kähler quotient of this open subset of the vector space, what you get is precisely complex hyperbolic space endowed with its standard symmetric metric. So we see that complex hyperbolic space is perhaps a very simple example of a PSK manifold. Okay, so given a Kask manifold, we've seen how we can form a Kähler quotient, but conversely, we can also consider bundles over the Kask manifold. In particular, we can consider the cotangent bundle of a Kask manifold. Now, the cotangent bundle of a Kask manifold turns out to carry a very nice structure. Using the special Kähler connection nabla, we can split the tangent bundle to this cotangent bundle as a direct sum of pullback of the tangent bundle downstairs plus pullback of the cotangent bundle, and then define the following three tensor fields: G, which of course will be a metric, which is just built out of the standard or the metric on the underlying Kask manifold and its dual; I1, which is built out of the complex structure and its dual; and I2, which is built out of the Kähler form. Here, we regard the Kähler form not as an skew symmetric, well, not as a two form, but as an isomorphism between the tangent and cotangent bundles of the Kask manifold. And in that sense, we can interpret it here as an endomorphism of this direct sum. And it turns out that these three tensor fields define a pseudo hyperkähler structure on this cotangent bundle, which we will denote by n, if and only if the initial data that we started with defined an affine special Kähler manifold. Of course, we also have the conical structure. So we have the vector field psi and j psi. And this is precisely what gives rise to a rotating circle action. Namely, by taking minus j psi, the minus is just there for conventions, and taking the horizontal lift with respect to the special Kähler connection, we obtain a circle action on the pseudo hyperkähler manifold, which is rotating. Okay, so this is how we produce a pseudo hyperkähler manifold, which is with a rotating circle action. And note that the signature also is the type that we want, because the complex signature of a Kask manifold is n,1. So the quaternionic signature of this G is always going to be n,1 as well. Now, one final remark about these hyperkähler manifolds is that this hyperkähler metric is called semi-flat, because if we restrict it to the fiber over a fixed point in the Kask manifold, we get a half-dimensional submanifold, which is just the cotangent space to that point. And when you restrict it to that submanifold, you see that the coefficients of the metric are constant. They do not depend on which point in the fiber I'm at. So this metric is flat when we restrict it to this half-dimensional submanifold. That's why these hyperkähler metrics are sometimes called semi-flat. Okay, so this is how we produce pseudo-hyperkähler manifolds of the type we're after. And we can put this all together into the following diagram. Let's start with a Kask manifold of dimension 2n plus 2, real dimension 2n plus 2, m. We can take on the one hand the Kähler quotients to form a PSK manifold m bar. And on the other hand, we can form its cotangent bundle, which will be of real dimension 4n plus 4. And we'll have a pseudo-hyperkähler structure of the desired type. So we can apply the HKQK correspondence to it. This will yield a quaternionic Kähler manifold n bar, also of dimension 4n plus 4. So we see that given a Kask manifold, or equivalently a PSK manifold, we have a quaternionic Kähler manifold of negative scalar curvature. And that completes this diagram. This map is called the C-map. I told you that the Kask manifold and PSK manifold will be equivalent for us. And the reason why one considers the C-map as a construction whose input is a PSK rather than a Kask manifold is that it turns out that this final quaternionic Kähler manifold here is a bundle over m bar always, but not over m. So it's more natural to consider this as a map that takes in a PSK manifold and spits out a quaternionic Kähler manifold rather than taking in a Kask manifold. So in conclusion, we've seen that the C-map produces a quaternionic Kähler manifold of negative scalar curvature out of any PSK manifold. Now, why is this so great? Well, that's because PSK manifolds are easy to construct. A PSK manifold, in fact, it can be built up out of very flexible initial data. So there's a PSK manifold associated to any C star invariant domain inside a complex vector space, endowed with a holomorphic function of degree 2 with respect to the C star action. So this is a very flexible set of data, satisfying if we have to, we have to also require one non-degeneracy condition, but that's an open condition. So despite this condition, the data is still very flexible, and associated to any type of data like this, we get a PSK manifold, and therefore a very rich source of quaternionic Kähler manifolds. Okay, there's one more thing which I have neglected to tell you so far, which is the following. So I told you that the input for the HKQK correspondence was a pseudo-hyperkähler manifold endowed with a rotating circle action and a Hamiltonian function fz. Now, as you all know, a Hamiltonian function is never unique in the sense that we can always add a constant to any Hamiltonian function and obtain another Hamiltonian function, which will do just as well. And in this way, we see that the HKQK correspondence actually produces a full one-parameter family of quaternionic Kähler manifolds out of one fixed hyperkähler manifold by just varying the Hamiltonian function. In the context of the C-map, the Hamiltonian function fz is given by this formula. So we see we have a canonical choice, which is just -1/2 times the norm squared of z. And then we can add some constant c, any real constant will do, and obtain a one-parameter family of quaternionic Kähler metrics out of a single PSK manifold. The corresponding, or the output metrics will be denoted GC. Fundamental fact about these C-map metrics is that if the initial PSK manifold m bar was complete, then under some minor technical assumptions, which are verified in all known examples, and I don't really want to get into, these resulting quaternionic Kähler metrics are going to be complete for all non-negative values of the deformation parameter C. So we get an entire one-parameter family of complete quaternionic Kähler metrics, starting from any complete PSK manifold. One small remark I would like to make is that G0, so when I choose C equals to 0 in this formula, I get one metric, which is known as the undeformed C-map metric. And if I choose a positive value for C, the corresponding metrics are known as deformed C-map metrics. An important fact about these deformed C-map metrics is that they are all locally isometric. So if I choose two positive values, C and C prime, then the metrics GC and GC prime are going to be locally isometric in the sense that their universal covers are isometric. So the local geometry really only depends on whether C is equal to 0 or C is positive. Okay, so I appreciate that this is all a lot to take in. So let's return to our simple example, the PSK manifold complex hyperbolic space CHN, and the associated Kask manifold, which was nothing but an open subset of Cn, 1, by which I just mean Cn plus 1 denoted with, or endowed with the flat scalar structure of signature n,1. The cotangent bundle of this Cas manifold is just going to be an open subset of H n,1, which we think of as the cotangent bundle to C n,1, which is endowed with a flat pseudo-hyperkähler structure. And the rotating circle action acts on the first coordinates, which parameterize this C n,1 by rotations, the minus again being conventional, and leaves the fiber coordinates invariant. So we have a very simple, almost trivial hyperkähler structure here. And one may ask, can I actually expect to get something interesting here on the quaternionic Kähler side of the correspondence? The answer is yes. Even for this very simple initial data, the undeformed CMAP produces an interesting space, namely it produces a non-compact Wolf space, so a non-compact quaternionic Kähler symmetric space, which is the dual of the Grassmannian of complex 2 planes in C n+1. So this is a symmetric space, and the deformed CMAP metrics then determine a one parameter deformation of the symmetric space through complete quaternionic Kähler manifolds. Okay, so that's all I want to say about the general CMAP construction. The next thing I want to discuss is symmetries of these quaternionic Kähler manifolds that one produces using the CMAP. All right, so as before, I'm going to start by discussing the HKQK correspondence rather than the CMAP in general. So the first thing we want to understand is how to carry a symmetry of a pseudo-hyperkähler manifold endowed with rotating circle action over to the corresponding quaternionic Kähler manifold n bar. For this, let's introduce some notation. We say that the vector field on such a pseudo-hyperkähler manifold endowed with omega 1 Hamiltonian and rotating circle action lies in the infinitesimal automorphism algebra of this manifold if it preserves all of this data. So it has to preserve the pseudo-hyperkähler structure, the generator of the circle action, and the Hamiltonian function fz. And we're going to denote the killing algebra of the quaternionic Kähler manifold by isom of n bar. Then the first theorem, proven together with Cortés and Saha, is that there exists an injective linear map from the space of infinitesimal automorphisms of the pseudo-hyperkähler manifold with rotating circle action to the killing algebra of the quaternionic Kähler manifold. Moreover, if we start with a k-dimensional subalgebra of infinitesimal automorphisms, then the result of applying this injective linear map is a bunch of killing fields which generate a k+1 dimensional subalgebra of the killing algebra of the quaternionic Kähler manifolds, which takes the structure of a possibly trivial central extension of the original subalgebra. So this map is not quite a Lie algebra homomorphism, but it's very close to it. Okay, so let's see the sketch of proof. We start with such an infinitesimal automorphism. Then by construction, it will be a killing vector field with respect to this modified metric GH, which I introduced before. However, as I said before, twisting will destroy differential conditions. So upon twisting, the twist of X will not preserve the twist of GH, which is the quaternionic Kähler metric. So we need to modify X first, so that the twist of the modified vector field will be a killing field. So our ansatz for the modification is to add a term which is of the form a function psi times z, the generator of the circle action. And we're going to interpret the condition that the twist yields a killing field as a differential equation for this psi, which one can write down explicitly in terms of the twist data. And the question then becomes whether you can solve these differential equations. And we show that indeed one can, and do so explicitly. Now, the reason why one doesn't obtain a Lie algebra homomorphism in this way is because, first of all, we did this modification. This messes a bit with the commutators. And secondly, commutators are also not preserved upon twisting. So the combination of these two effects, our modification and the effect of twisting on commutators, ensures that in general one obtains a one-dimensional central extension rather than a isomorphic subalgebra. So let's see how this works in an important example. In the case of the CMAP, I told you that these pseudo-hyperkähler metrics we have are semi-flat, right? So we have constant coefficients of the metric if we restrict to this half-dimensional submanifold that is the fiber over a fixed point in the Cas manifold. Now, given this, we see that there's an isometric action of R2n+2 just given by translations in these fibers, right? In fact, this action of R2n+2 satisfies all the requirements for it to be defined infinitesimal automorphisms. And so we can twist this action to an action on the corresponding quaternionic Kähler manifold. And what we get will be, well, a one-dimensional central extension of R2n plus 2. And what does one think of if one hears that? Of course, one thinks of a Heisenberg algebra. Right? So integrating up, we see that we obtain, in fact, a locally free and isometric action of a Heisenberg algebra, or a Heisenberg group, sorry, of dimension 2n plus 3 on any quaternionic Kähler manifold that arises from the CMAP. And this is true for all values of this deformation parameter C. And that's the case because this HKQK correspondence is valid for all values of this parameter at the same time. Okay, so we see that quaternionic Kähler manifolds that arise from the CMAP always have this Heisenberg action. This was a fact that was already known and proven from different perspectives before. But it's nevertheless important. I told you that these CMAP spaces can be regarded as bundles over the PSK manifold that you started with to produce them using the CMAP. And it turns out that this Heisenberg group we just discussed acts fiber-wise, so preserves the fibers of this bundle structure. And therefore, a natural question given this is, can we find additional isometries of these CMAP spaces which cover non-trivial maps on the base PSK manifold, right? And the answer is yes, of course, otherwise I wouldn't be telling you this. And a way to do this is to start with a symmetry of this PSK manifold in the appropriate sense and lift it to an isometry of the quaternionic Kähler manifold. That's what I'm going to explain how to do next. So first, let's define what the symmetry is in this setting. We have a PSK manifold, or equivalently a Kask manifold. Given a Kask manifold, an automorphism of the Kask structure is of course a diffeomorphism of the manifold, which preserves the pseudo-Kähler structure, the special Kähler connection, and the Euler field. And given that, it always descends to the Kähler quotient M bar, so to the corresponding PSK manifold, and induces the diffeomorphism there. And by definition, that will be a PSK automorphism. So given this extrinsic definition of PSK manifolds that we have, this extrinsic definition of symmetry also is quite natural. Given such a symmetry, infinitesimally, so an infinitesimal automorphism of a PSK manifold, the next theorem, also proven with Cortés and Saha, states that we can always lift it to a killing field on the corresponding CMAP space N bar. And again, this statement is true for all non-negative values of the deformation parameter. So one word about the proof. As we already saw, it suffices to check that we obtain infinitesimal automorphisms of the corresponding pseudo-hyper-Kähler manifold with rotating circle action. And this is easily done. We start on the PSK manifold. We have an infinitesimal automorphism there. First, we lift it to the Kask manifold M. And then, using the pullback on one forms, we can canonically lift such a vector field to its cotangent bundle and check that the lifted vector field indeed defines an infinitesimal automorphism of the full structure there. So that's how the proof proceeds. All right. There are some interesting corollaries which have quite strong implications for CMAP spaces. In particular, for every non-negative value of the deformation parameter, we get a very strong bound on the dimension of the isometry group of the CMAP space. So the dimension bound that we get is that the dimension is at least equal to the dimension of the automorphism group of the PSK manifold plus 2n plus 3. This 2n plus 3 comes from the 2n plus 3 dimensional Heisenberg group, which acts fiber-wise and therefore is independent of these lifted automorphisms of M bar. Therefore, we can just add the dimensions. A second corollary is that if the automorphism group of the PSK manifold acts with cohomogeneity K on the PSK manifold, then the corresponding CMAP space will be of cohomogeneity at most K plus 1 for any non-negative value of C. The reason is that, okay, we have cohomogeneity K acting on the base of this fiber bundle, and we have this Heisenberg group of dimension 2n plus 3 acting on the fibers. Now the fibers are of dimension 2n plus 4, so the Heisenberg group acts with cohomogeneity 1. Putting these two actions together, we see that the cohomogeneity of the total space is at most K plus 1. Okay. So let's apply this once again to our running series of examples. Start with complex hyperbolic space, which is a PSK manifold, and it's acted on transitively, as we all know, by the special unitary group of signature n,1. Now, this group acts by PSK automorphisms. So our theorem tells us that we can lift this action to the corresponding quaternionic Kähler manifolds. And therefore, we see that this one parameter deformation of the non-compact Wolf space consists of complete quaternionic Kähler manifolds whose cohomogeneity is at most 1, because the cohomogeneity of the initial PSK manifold was 0. Okay, So now we have a series of examples which are of cohomogeneity at most equal to 1. And the next natural question is to ask, okay, how do we prove that the cohomogeneity is exactly equal to 1? Or more precisely, how do we prove that these manifolds are not locally homogeneous for positive values of the deformation parameter? Well, there's a very simple way to do that, at least in principle, namely to compute a non-constant curvature invariant, because the curvature is invariant under isometries. So if I can compute a curvature invariant and show that it's non-constant on my manifold, then certainly that manifold cannot be homogeneous, right? So that's a very simple principle, but it turns out to be quite difficult in practice. Again, we use the HKQK correspondence to express the curvature tensor of the quaternionic Kähler manifold in terms of the hyperkähler data on the dual hyperkähler manifold. So the initial hyperkähler structure and the two-form omega h, the Hamiltonian functions, etc. And the twist formalism gives you a way to do that, but the initial formula one obtains is hugely complicated. It fills an entire page, basically. And so one has to really do a lot of work to bring it in any kind of workable form and get the formula that's actually useful for computations. This is so complicated that, in fact, an entire paper of ours is dedicated to it. The main result of that paper is the following formula, which is displayed here. So we start again with a pseudo hyperkähler manifold with omega 1 Hamiltonian rotating circle action, as always. And we say we have the curvature tensor of the dual quaternionic Kähler manifold. It's the twist of a tensor field on the hyperkähler manifold. This tensor field is called R tilde. And here we give an expression for this R tilde. Now, I don't want you to try to understand the full details of the formula. I just want you to see qualitatively, first of all, the formula is manageable. It is practical. And secondly, it features here the curvature tensor of the hyperkähler manifold you started with. It features this deformed metric GH, the two-form omega h, and the complex structures IK also make an appearance, as well as the Hamiltonian functions Fz and Fh. So we see that all the ingredients come together in a more or less simple way. Okay, so how about some applications of this formula? Let's try to compute curvature invariance with it. And that's exactly what we did. We returned to the series of examples that we have been studying all this time. So we again apply the CMAP to complex hyperbolic space. I've now shifted the index from n to n-1 here. So n bar is a 4n dimensional quaternionic Kähler manifold, not 4n plus 4 dimensional now. And what we did is we computed the Hilbert-Schmidt norm of the curvature operator of the quaternionic Kähler manifold. This is a function on the quaternionic Kähler manifold, and it is related, or it's the twist of a function on the hyperkähler manifold, which we can express as follows. This is the full expression. Now note that for c equals to 0, Fz and Fh are equal up to sign. So this will just be a -1, and this whole expression collapses down to something much simpler. So we see that for c equals 0, we get a constant, as it should be, right? Because we know that for c equals 0, we have a symmetric space. So any curvature invariance had better be constant. For positive values of c, however, the situation is much more interesting. There, this quotient Fz over Fh is not constant. And in fact, it turns out that this formula R squared defines an injective function of exactly one of the coordinate functions in a suitable global coordinate system on the quaternionic Kähler manifold. And what that means is that the level sets of this coordinate function are preserved by any isometry of this metric. In particular, the metric is of cohomogeneity at least equal to 1. So combining that with our earlier result, we obtain the theorem that this series of examples is of cohomogeneity precisely equal to 1 for all positive values of the deformation constant and for all natural numbers n. Okay, so this gives us an explicit series of cohomogeneity 1 examples. And these are in fact among the first known examples of complete quaternionic Kähler manifolds of cohomogeneity 1. They're not quite the first. There are some other series of examples that have also been constructed using the CMAP. However, they are the first series that makes use of this deformed CMAP metric. The previously known series of cohomogeneity 1 examples is created by starting with a cohomogeneity 1 PSK manifold and then applying the undeformed CMAP. So this is the first time the deformed CMAP is used. And in particular, this series of examples shows that this deformation, which is sometimes called the one loop deformation because it has some origins in theoretical physics, this deformation is highly non-trivial. This is a proof of concept of this fact. In fact, I would go much further than that. I would conjecture the following. Say we start with any homogeneous PSK manifold. not just a complex hyperbolic space, but any homogeneous PSK manifold, and we apply the CMAP, and we consider these deformed CMAP metrics, then I conjecture that the deformed CMAP metrics GC, where C is positive, are of cohomogeneity precisely 1. So that's a natural generalization of our result, and we are working to establish this result for some other series of examples as we speak. Okay, so that's all I want to say about the cohomogeneity 1 examples. And as I promised, the last part of my talk will be about discrete quotients of these cohomogeneity examples, cohomogeneity 1 examples. So what we've done is constructed a whole bunch of killing fields. In fact, we have constructed a subalgebra of the killing algebra, which is isomorphic to a semi-direct product of a special unitary group and a Heisenberg group, right? And integrating these killing fields up, which we can do because the manifold is complete, we get a group of isometries acting on our manifold by cohomogeneity 1. Let's call this group G. Now, the next step is to consider discrete quotients of G. Now, why is this interesting? Well, first of all, discrete quotients of these quaternionic Kähler manifolds, or correspondingly discrete subgroups of G, can be used to construct complete quaternionic Kähler manifolds which have non-trivial and interesting fundamental groups, if we can find some interesting discrete subgroups of G. And the second interesting aspect of such constructions is that the resulting quaternionic Kähler manifolds might have non-trivial volume properties. Ideally, one would hope for manifolds with finite volume. This would be the goal, the ultimate goal. Such manifolds are also very interesting from the point of view of theoretical physics, because recently there has been a bunch of conjectures, the so-called swampland conjectures, which assert that certain quaternionic Kähler manifolds which show up in the context of string theory as certain moduli spaces should be of finite volume. So there's an expectation from theoretical physics that there should exist quaternionic Kähler manifolds of finite volume. However, no such examples beyond the locally symmetric spaces are known at present. So it would be interesting to see if one can make any kind of progress in the direction of these conjectures. Okay, so given that we're looking for discrete subgroups, we're of course interested mostly in discrete subgroups which are as large as possible, by which I mean there should be lattices inside the group G, and ideally even co-compact lattices, so that the quotient will be a compact space. Okay, so we have this group G acting. It doesn't quite act effectively, but if we pass to a cyclic quotient, which I'll denote by n hat, then in fact we get an effective action of this nice group SU1, n-1, semi-direct product with the Heisenberg group of dimension 2n plus 1. Now, if we're looking for discrete subgroups or lattices inside this group, one can try to look for arbitrary lattices, but what we did is we looked for lattices of a specific type, namely lattices gamma hat, which are of a semi-direct product form, where we take a lattice inside the special unitary group gamma 1, which normalizes a lattice inside the Heisenberg group gamma 2, and take the semi-direct product of these two lattices to obtain a lattice in the semi-direct product group. So the question now becomes, can we find a lattice inside the special unitary group that normalizes a lattice inside the Heisenberg group? And that's the content of the following theorem, together with Cortés and Röser, and that for n equals to 1 and n equals to 2, we can in fact construct infinitely many non-isomorphic co-compact lattices gamma 1 and gamma 2 of the above form, and so we get a co-compact lattice gamma hat inside G hat. And for larger values of n, so every n at least equal to 3, we obtain infinitely many lattices, which are however not co-compact, because the lattice inside the special unitary group gamma 1 is not co-compact, even though it does normalize a co-compact lattice inside the Heisenberg group. Okay, so let me say a few words about the proof here. The case where n is at least equal to 3 follows easily from some known results about lattices in Lie groups. So there are some results by Mosak and Moskovich, which we use to easily deduce this result. So most interesting are the case n equals 1 and n equals 2. In fact, the case n equals 1 is rather simple, because in this case, this unitary group is trivial. So all one is left with is the three-dimensional Heisenberg group. And of course, we can construct infinitely many co-compact lattices inside the three-dimensional Heisenberg group. This is not very hard. The case n equals 2, however, is a lot more complicated. In that case, we're dealing with SU1, which we all know is isomorphic to SL2R. And discrete subgroups inside SL2R are known as fuxillion groups. So what we're really looking for are co-compact fuxillion groups. Now, there are many classical construction methods for fuxillion groups. And we use one of them, namely the theory of quaternion algebras, which is a certain arithmetic construction, to construct infinitely many examples of Cocompact fuxillion groups, which we can show explicitly preserve a lattice inside C2. Now, this helps us because we can think of the 5-dimensional Heisenberg group as C2 plus R, at least as a vector space. And then we can start with this lattice in C2 and check the subgroup that it generates inside this 5-dimensional Heisenberg group and see that it really generates a discrete subgroup inside the full 5-dimensional space. And that's what we did to obtain these examples. Well, as an easy corollary now, given these discrete subgroups, up to passing to some finite index sublattice and some other simple technicalities, we obtain as a corollary that for any natural number n and for suitably chosen positive values of c, we get discrete quotients of these cohomogeneity 1 examples, which are diffeomorphic to a real half-line times k, where k is now a locally homogeneous space, which always has finite volume. In the cases n equals 1 or 2, we can even choose k to be compact. Here, the suitably chosen c bigger than 0 is not very essential to us because, as I mentioned earlier, for different positive values of c, the local geometry of the spaces or of the matrix GC is the same. So we don't really mind having to cherry pick our values for c. As I said, I'm also interested in the volume properties of these quotients. So that's what my final result here will be about, also proven with Cortés and Röser. Let's consider one of these quotients, x. So it's a quotient of this manifold n hat by a lattice gamma hat. And it's diffeomorphic to a real half-line times a locally homogeneous space of finite volume. And let's fix some real positive number lambda and consider the subset of x where we allow the coordinate in the real half-line to be larger or equal to lambda or smaller or equal to lambda. That gives us sort of a partition of x into 2 parts. And then we computed the volume of these 2 parts. And we saw that independent of the choice of lambda, you started with one of the parts, namely the part where the coordinate is at least equal to lambda, is always of finite volume, while the other is of infinite volume. So what we see is that you somehow have an infinite and a finite volume part. And if we can choose our k to be compact, so the case n equals 1 and n equals 2, then we can speak of 2 ends of our manifold, one of which is an end of finite volume and the other of which is an end of infinite volume. So we see that in dimensions 4 and 8, we have now obtained infinitely many examples of complete quaternionic Kähler manifolds with a finite volume end, which are not locally symmetric spaces. And certainly in dimension 8, these are the first known examples of this type. So that's the last thing I wanted to say. And therefore, I would like to thank you all for your attention and ask if there's any questions, etc.
Well, thank you very much for a really interesting talk. Are there questions? Do you see the finite volume question in reach, or do you think what's your thoughts?
It's an interesting story because it involves a little bit the physical interpretation of these spaces. So this whole CMAP construction was inspired originally by theoretical physics constructions as well. That's where the name CMAP comes from. And these deformed CMAP metrics I've been discussing, they have in physics an interpretation of a moduli space which is partially quantum corrected, but not fully quantum corrected. And what the physics expectation is that once you modify the space further by adding the full quantum corrections, then the space should be a finite volume. So physically, the expectation is not necessarily that these spaces should reach finite volume, but there should be some kind of very non-trivial modification of these spaces which do allow for finite volume quotients. So it's not directly in reach, but I think this is both mathematically and physically sort of the first step in the right direction, which will bring us there hopefully in the end.
Yeah. Nice.
I see a raised hand.
Hi, can you give me an example of one of these Ks, one of these compact Ks? Are these nil manifolds or something? What are these Ks?
so it's a, well, so these Ks are quotients of, so you have the just R2n plus 3, and you have now this lattice inside the unit. So we have this, so here we have these lattices inside the special unitary group constructed, let's say, using quaternion algebras, which is they're arithmetic lattices. And such an arithmetic lattice, in the examples we consider, preserve a certain lattice in the Heisenberg group. And then we have the semi-direct product of this. This semi-direct product is then what we quotient out of our manifold. And so these lattices are rather complicated. They're not just nilpotent or something like that. They are sort of a mix of a lattice inside the nilpotent Lie group and a lattice inside this unitary group.
I mean, so one of these Ks.
Sorry?
So one of these Ks will be three-dimensional, is that right?
Exactly. So in the case
one example will be three-dimensional, is that right?
Yeah. Yes, that's right. And in fact, I should have said that. In the case n equals 1, we are just considering a lattice inside the Heisenberg group. So this is a nil manifold. So in that case, we just have a nil manifold. In the case n equals 2, which I think is the more difficult case, there it's much more complicated, and we don't necessarily have a nil manifold. But the case n equals 1 is a nil manifold. You're right about that.
But I mean, I'd be interested to know, more exactly what this.
I think the connection.
Oh dear.
Ooh.
Oh dear.
Okay, I think we're back. Now you're muted, I think.
Yeah, thank you very much. I'm sorry, I don't have a clear connection, but thank you very much for the question, for the answer.
Okay, thank you.
And for the talk.
Yeah, thank you very much.